Today we're going to learn about graphing rational functions with transformations. By the end of this video, you should be able to find the asymptotes, intercepts, and end behavior of rational functions and be able to graph rational functions. First, before we start learning how to graph, we have to learn what an asymptote is. An asymptote is a line that the function approaches and usually doesn't touch. So let's start by looking at the general form of a rational function. We have y equals a divided by x minus h plus k. So if you think back to what we did at the beginning of the year, we talked about a, h, and k, and a, h, and k affect the graph in the same way now as they did then. So a will stretch the graph. H will move the graph horizontally. And K moves the graph vertically. Now, let's take a look at the parent function. So our parent function for rational functions is y equals 1 over x. So in this case, we have that a is 1, h is 0, and k is 0. Now, every rational function has a vertical asymptote. So this is going to be a vertical line, and if you remember back to Algebra 1, vertical lines are always x equals a number, and vertical asymptotes occur where the denominator of the function is equal to 0. So if I take the denominator, which is x, set it equal to 0, and solve, then I will get my vertical asymptote. So for the parent graph, our vertical asymptote is x equals 0. In general, you will have a vertical asymptote at x equals h. Now, when we draw our vertical asymptotes, you want to use a dotted line. The next thing we need to find is a horizontal asymptote. And your horizontal asymptote is going to be y equals k. So for our parent function, that asymptote is y equals 0. Again, you want to draw your asymptote with a dotted line. Now, to graph my function, I'm going to make a table. So I'm going to pick x values and then plug x into our function to see what the y value is. So if I pick -2, -1, -1/2, 1/2, 1, and 2 as my x values, and I plug them into this function, 1 over -2 is -1/2, 1 over -1 is -1, 1 over -1/2 is -2, 1 over 1/2 is 2, 1 over 1 is 1, and 1 over 2 is 1/2. So now I'm going to plot these points. Now, we said that an asymptote is a line that a graph approaches but doesn't touch. So when I connect these dots, they are going to get closer and closer to the horizontal asymptote and closer to the vertical asymptote, but never cross it. So we have actually two parts to our graph. And if you go to the calculator, you can double check. If you go to y equals, alpha y equals to get a fraction, 1 over x, and graph it, you can see that this graph on the calculator matches the graph that we created by plugging in x values. So our domain is the set of all x values, and this is going to be the same kind of method that we used when we were doing rational expressions and solving rational equations. You want to see what makes the denominator 0. Well, that's the same thing that we did when we were finding the vertical asymptote. So since our vertical asymptote was x equals h, our domain is always going to be the set of x's such that x does not equal h. So in this case, it's set of all x's such that x does not equal 0. Similarly, the range is related to the horizontal asymptote. So our range is always going to be y such that y does not equal k. So for this problem, the range is y such that y does not equal 0. Okay, and you can verify that by looking at the graph. On the graph, if you look at how low the graph goes, this left branch of the graph goes all the way down to negative infinity and then gets really, really close to 0. The right branch of the graph goes up to positive infinity and then gets really close to 0. But neither branch ever touches the x-axis, so it is never equal to 0. Lastly, we have our end behavior. So we remember that we write our end behavior as x approaches infinity, f of x approaches blank, and as x approaches negative infinity, f of x approaches blank. Now, if you look at the left side of the graph and the right side of the graph, on both ends, the graph is approaching the horizontal asymptote, which is 0. So this is our parent function. Let's take a look at how a, h, and k affect this graph. So here we have y equals 1 over x minus 2 plus 1. So our a is 1, our h is 2, and our k is 1. Now we said that our vertical asymptote is always x equals h, so this is x equals 2. And we can graph that. We said that our horizontal asymptote is always y equals k, so we can graph that. Then to graph the points, I'm just going to go to the calculator. Now if I type in my equation, alpha y equals, enter, 1 divided by x minus 2 plus 1, and then I go to the table, which is second graph. I want to find a couple points that are easy to graph. So for example, 1, 0 is an easy point to graph. So is 3, 2. So let me graph those. So you can see that these 2 points are going to be on the separate branches of our function. So I'm okay with you graphing it this way as long as you have 1 point on each branch of the function. If you want to make your graph more exact, you can look for other fractions that aren't too bad to graph. So 0, 1/2 is fairly easy to graph, as is for 3/2, and 3/2 is 1.5. Okay, and then you can just sketch in the curve. Make sure that your graph approaches the asymptote, but never touches it. So then our domain we said was related to the vertical asymptote. So our domain is going to be x such that x does not equal 2. Our range is related to the horizontal asymptote. So our range is going to be set of all y such that y does not equal 1. And then our end behavior, I'm going to show you a shortcut to writing end behavior. Since both ends of the graph approach the same number, they approach the horizontal asymptote, I can write my end behavior as x approaches plus or minus infinity. F of x approaches the horizontal asymptote, which is 1. This means that both the left and the right side of the graph approach 1. Let's look at another example. Here we have y equals negative 1 over x minus 1 minus 3. Since we have a negative out front, our a is going to be negative 1, our h is 1, and our k is negative 3. So we said that our vertical asymptote is always x equals h. We can graph that. Our horizontal asymptote is always y equals k. And we can graph that. Now, again, I'm going to go to the calculator to get the points to graph this function. So we have negative 1, x minus 1, minus 3. So you want to find any points that have integers. So I have 0, negative 2, and 2, negative 4. Okay. Since those are in different quadrants, we know that those are going to be on different branches of the graph. And let me point out one other thing. Where this says error, that tells you where your vertical asymptote is, because if you try to plug 1 into this equation, you're dividing by 0, so you get an error. So now I can sketch in the branches of the graph. They should get closer to the vertical and horizontal asymptotes. Now, you'll notice that in this graph, the graph is in the top left and the bottom right, whereas the other graphs were in the top right and the bottom left. And that's because A is negative. It's switched which quadrants the graph is in. Now, we said that the domain is related to the vertical asymptote. So our domain is x such that x does not equal 1. And our range is related to the horizontal asymptote, so that will be y such that y is not equal to 3. For our end behavior, both ends are approaching the horizontal asymptote, so we can write our end behavior as x approaches positive and negative infinity, f of x approaches negative 3. Let's do one more problem. Here we have y equals 2 over x plus 3 minus 2. So our a is 2, our h is negative 3, and our k is negative 2. Now this problem is set up a little bit differently, but it's the same information. Sometimes on the SOL you will see drag and drop problems like this, where you are supposed to choose what the vertical and horizontal asymptotes are. And you need to be careful that you get the right asymptote in the correct box. So we said that our vertical asymptote is x equals h. So that's x equals negative 3. We can draw that in. Then we said our horizontal asymptote is y equals k. We can draw that on our graph. Then we're going to go to the calculator to fill in the points. So we have y equals 2 over x plus 3 minus 2. If we go to the table, sometimes you have to scroll a little bit. So I see 4 points that are integers. I have negative 5, negative 3, negative 4, negative 4. And then I also have negative 2, 0, and negative 1, negative 1. Okay, and then I can connect those points, making sure that my graph approaches the asymptotes. Now remember that my domain is related to the vertical asymptote, which is x, such that x does not equal h, which is negative 3. My range is related to the horizontal asymptote, so I have y such that y does not equal k, which is negative 2. And both ends of my graph are approaching the horizontal asymptote, so I can write my end behavior as x approaches positive and negative infinity, f of x approaches negative 2. And that is how you graph rational functions using transformations.